If you are a scientist, or you are training to become a scientist, or you want to become a scientist, this video is for you. These are my top 5 tips that every scientist should know. My name is Ben Ryan. I'm a neuroscientist by training. I've done a PhD. I did a postdoc at Stanford. I published over 20 peer-reviewed scientific papers. And these are the 5 most important things that I learned in my scientific training that everyone should do for their career. Some of them I was taught, others I learned through experience, but I can assure you that all 5 of them, if you follow them, will support your career. Without further ado, let's dive right in. Number 1, do every single experiment. That might sound confusing. You're probably thinking, I can't possibly do every single experiment. What is this guy talking about? I don't mean to literally do every single possible experiment. That's obviously a huge waste of energy, time, and resources. What I mean by that is when you're leading a project and your paper is starting to come together, all the progress in your project is based upon key findings, right? You don't have a project at all until you have some interesting result, right? Based on that result, you decide what experiments you should do next. And usually you're trying to ask the next obvious question. But what I'm saying is you should stop once you have a result and ask all of the important supporting questions. If there are specific control experiments that you could do that would enhance the confidence in your findings, do them. If you have other techniques in the lab that you could do to ask the same scientific question but provide additional evidence that would support your conclusion, do it. What I'm saying is do every experiment that you can possibly think of surrounding that one key finding that really makes it look like it's actually true. I think an example might help here. Dr. Monique Smith, a researcher now at University of California, San Diego, in her PhD, she discovered something amazing, that when mice spend time near other mice that are in pain, the mice start to act as if they too are in pain. They were somehow absorbing the pain of other mice. So that began as her first key finding. Now, what questions immediately come to mind? One question that comes up to me is, how do you know that it's actually the other mice causing the pain and not something else? Okay, simple solution. You might do an experiment where you house the mice in different rooms and you detect if it's something else in the environment that's causing them to act like they're in pain. Makes peer reviewers more confident in your conclusions. That's an extremely easy control experiment to do. Might as well do it. Okay, now a second question. How do we know that they're actually taking on the pain of the other mice and not just mimicking it? Great question. Dr. Monique Smith had a clever solution. She designed a control experiment where she basically terminated the pain of the first mice. You can imagine it like giving them painkillers. If the bystander mice were really just mimicking, then you would think that they would stop acting like they were in pain immediately. But they didn't. Their pain persisted for several hours after, suggesting that it wasn't just mimicry, they were actually experiencing something. In your projects, whenever you have the opportunity to do these control experiments, even if they're going to go in the supplemental figures, you should do them. Another great supportive experiment that Dr. Smith could have done and did do is to test their pain using other pain measurements. They might show hypersensitivity in one type of pain measurement, but what about the others? Again, these are just great supportive and simple experiments that you can do to make your research more robust. So why do these? The reason why this is important to do is because it doesn't just make your research better and make your conclusions appear more valid. And yes, it genuinely does make your research more rigorous, but it also supports you in publishing in high-level journals. You might notice that all the papers in Science and Nature and Cell all have like 50 supplemental figures. Those are all those additional control experiments that support the conclusions made in the main figures. And it's important that you do those experiments not after the peer reviewers ask you to, but before you even submit. The purpose of peer review is to identify any major flaws in your research and make you answer any open questions. Now answer me this. If you submit a paper to a journal and the peer reviewers look and you've already answered every potential question through all these supplemental experiments, what are they going to do? They will have fewer questions to ask you, and so you're more likely to be accepted for publication in that journal. This is like the #1 cheat code for publishing papers in high-level journals. Do all the control experiments. Not only does it increase your chances of publishing in good journals, but it also makes your research genuinely more rigorous. Okay, number 2. Do the experiment that scares you the most. This is something that my former mentor, Dr. Rob Malenka, taught me at Stanford. In every project, there's an experiment that scares the hell out of you. That's because every project is built around some key finding. If you have some interesting finding that you're building your entire paper around, your biggest fear is that another experiment will come along and prove that what you think is going on is actually wrong. That's the experiment that you should do first, the experiment that scares you the most. Once again, this not only makes your research more rigorous, but it also potentially saves you time. If you never do that experiment, you might literally spend years screwing around trying to figure out something that's actually not true, all because you refuse to complete this one experiment that would actually prove to you whether or not what you think is happening is really happening. If you're actively working on a project right now, you probably know exactly what I mean. You probably have an experiment in mind. You should do that experiment. It'll make you a better scientist, it'll make your research more robust, and it might save you time. And guess what else? There's a 50% chance that it'll be the answer you hope for. And even if it's not, it will lead you in the right direction. Okay, number 3. Practice your scientific writing. Learning to write scientifically is an important skill, and if you practice and perfect it, you'll write better papers, you'll write better grants, and you might even find yourself writing for media outlets. Plus, it might open publishing opportunities. If you publish good, clear papers, you might be invited by certain journals to write review articles, or it could create opportunities within your lab. When I was in my PhD, there were several people in my lab who had learned English as their second language. They did some great research, and when it was time to publish their findings, they just couldn't write the papers themselves. Scientific writing is an important skill that will never not be important, so please develop it as early as you can. Number 4. Write good titles and abstracts. There's so much to a scientific paper. Once you write your first paper, if you haven't yet, you'll totally understand. Introduction, results, methods, discussion, and there's so much to it, and so it's very easy to get sucked into the weeds. But the most important things are your title and abstract. Your title should convey your most important finding. It's literally okay to have your title be something like Variable A regulates variable B, and it does so through variable C. Those titles that are extremely clear and convey your findings are typically the best and most effective titles, because the title is the first thing that other people see when they decide, should I or should I not click on this paper? Now, if you have a good title and they click on your paper, what do they find next? Your abstract. If you're a scientist, then you know that a lot of the time when scientists are looking for articles to cite in their papers, they're starting with the abstract. They will make a decision whether they're going to read and sometimes even whether they're going to cite your paper based on just reading the abstract. So with that said, your abstract should answer several important questions. Number 1, what did you do? What experiments did you do? Number 2, what results did you find? And I'm not just talking about the key results. In your abstract, if you have the space for it, you should share any results that anyone might use to cite your paper. The more clear you make your results, the more likely your paper is to be cited. And nobody wants to have their paper never get cited. Your abstract should be clear enough that another scientist might cite it just from reading the abstract alone. And not to mention, when non-scientists go and start looking around the scientific literature, most of them don't have the academic credentials to get through the paywalls, so they often just look at the abstracts. It's therefore important to make sure that your abstracts are accurate and comprehensive. Next time you publish a paper, ask yourself, can a layperson read this and understand what's going on? Might they misinterpret something? Are the results and conclusions accurately portrayed? These are all important things to consider when writing abstracts. Okay, number 5. Apply to awards. Look, nobody's going to apply to awards for you. You might get nominated if you have a really supportive lab environment, but most of the time you have to apply yourself. And you should. There are probably numerous opportunities to apply for awards at the university level, at maybe the state level. If your university is part of a broader umbrella, for example, I did my PhD at SUNY Buffalo, State University of New York. You could apply to awards through SUNY, that umbrella, and even at the national level through organizations and foundations. The more awards you apply to, the more awards you're going to receive. And when you have those awards on your CV, it looks good. Be sure to highlight in your application every reason why you deserve this award. Don't half-ass it or be like, maybe I deserve it. No, you have to be super ambitious to be competitive. I know it might feel uncomfortable to be boastful and to put all your accolades in someone's face, but do it. That's how you win awards. You have to learn to market yourself. Okay, hold on. We have a bonus tip. Number 6. Get communications training. I believe that every graduate program in the sciences should have some level of communications training. I'm actually teaching a class at Stanford called How to Communicate Science for this reason. There may be courses like this at your university, but even if there are not, there are plenty of free resources online. You can find science communication trainings on the internet, in person, at specific conferences. You can also participate in competitions like the 3-minute thesis competition at your university, or the Mind Science Foundation, which I'm the chief science officer of, hosts a competition every year called Brainstorm, where you describe your research proposal to a lay audience and you can win up to $40,000. These aren't just competitions that you can win, these are actually training opportunities. Because when you participate in them, you learn to communicate. Trust me, if you have the opportunity to get some communications training, please take it. It's so important for so many reasons. First, it benefits science and society and the relationship between them. Look, science is very siloed. We work for years on our papers and then they get stuck behind paywalls and they're full of jargon, and if anybody from the general public, like your family members or friends, wants to read them, they pretty much can't. We need to open dialogue between science and society. Because when we fail to do that, it creates distrust. How can the public trust science when it's held behind paywalls and it's never accessible? So by getting communications training, we can help that relationship. Whether you're talking to your neighbor or your family member or someone on Facebook who's talking about how much they hate science, or a person at the bar next to you or sitting on the plane next to you, you are improving the relationship between science and the public by doing so. And you're going to be much more effective if you've had some training. Number 2, it's good for you and your career. When you learn how to communicate your work effectively, you level up as a scientist. You can write better papers. You can write clearer grants, which might result in more funding. You can design a better website that clearly communicates your research. If you find yourself, for instance, seated at a dinner table with a wealthy philanthropist and you can communicate your work, you're probably more likely to connect with them and you might get some research funding for your lab. And even if you decide to leave science, when you go to that job interview and they ask you, so what did you study? If you cannot communicate your research clearly, it will probably look bad. Whereas if you can, and you can get them to understand your work, it will connect with them and they will be impressed. Unfortunately, communications training is really not embedded in the scientific process. I really think it's on us as individuals to get that training, but the good news is once you do, it can benefit you in many ways. Not to mention, look what I'm doing right now. I'm on YouTube talking about science. You can put that training to use by getting on social media and posting about your research. This can create tons of opportunities. Being visible online as a scientist can open many doors. So I encourage you to seriously think about getting this type of training. All right, well, that has been my top 6 tips with the bonus tip. If you have more tips that you think others might appreciate, also put those in the comments. And of course, please subscribe for more science content. Thanks for your interest, and I genuinely wish you good luck in your career.